Okay, here we are. Um, well, it's our second round or our second video on the introduction to displacements, which is chapter 7. And I left off with elastic beam theory. I want to pick up where we left off. So let me go back to my screen, share my screen for you guys, and we'll pick up here. Okay, so we were talking about displacements, and we went through some introductory things about boundary conditions, slope, displacement. We even talked about some limit states. So now I want to give you some mathematical background, and this is called elastic beam theory. We'll use this, but you won't be responsible for the derivation of this. But I just think it's kind of interesting that you can see how this comes about. So we're going to start with considering how we can relate our moment, which you might remember is pretty important. We spent the whole semester talking about moment and deriving it, plotting it, doing a variety of different things, and always to set us up really for this part of the course. So we want to really worry about this moment part. So we're going to start with how moment is related to displacements in this beam. So let's consider a beam. You can see of length L. And like a lot of things that we do in this class, we're going to look at a little differential volume. You can see here dx wide of the beam. We're going to look at everything on these infinitesimal bits and pieces. So we're going to assume that the beam will bend into a curve, as you can see here. Now this looks circular, and it is for the segment, but the radius of this curvature for this segment, we'll call that rho, the radius of curvature, it's different as you go across the beam. So the beam is not required to bend into a circular arc. Just each little segment is. And as it does this bend, you can see it will pass through a very small angle we'll call d theta. So now let's see how a beam will bend. So in this case, we're going to look at a cantilever beam with a load P, and it's going to displace upward. So originally, remember our differential volume that we had before was dx, and now we're going to look at how this thing will stretch and actually get a little bit longer, and we'll call that the surface, so that'll be ds. Now, if we look at that at a really small level, differential level again, you'll notice that everything is very linear. So what we're going to do is look at how this changes as a function of the angle. So first, let's look at the tangent of the angle. So here's our angle theta. That's the same angle we talked about before, the slope of the beam, theta. So we know that the tangent of an angle is the change in the height, which is this vertical component, over the adjacent side, which is this horizontal component. So there's our kind of triangular shape. So again, at a point, we know as these things get really, really small that theta is related to y. Remember, y is displacement. That's what we're talking about. So that's how we get this relationship. Now, since the angles that our beams are deforming through are very, very small, they're so small that really the tangent of the angle is really the angle. So that's the first approximation in simple beam theory. So really the theta is just dy dx. Now that's not really very earth-shattering. If I told you that I could write a displacement function, y, and if I take the derivative of y, displacement, with respect to x, you get the slope of the line, slope. That's just kind of showing you where the geometry comes in. Okay, also from this geometry of the triangle, we can see that, again, this differential distance right here, d theta, can be given by the radius rho going through this arc. Again, a very small differential angle theta. So again, the arc length will be approximately equal to the radius rho going through that angle d theta. That seems a little out of touch right now, but what we're eventually trying to do is we're trying to relate curvature defined by rho to displacement. So if we go back to that previous expression and we divide both sides by ds and rearrange it, we just get this. And of course, we know d theta. I'm sorry, so that way, if we divide by ds, then the derivative of theta with respect to the surface is the curvature. So now we're getting a relationship between theta, which we know we can relate to displacement, and curvature. And we'll get curvature related to moment in just a minute. So again, so d theta ds represents this change in slope per unit length, and that's curvature. So the second approximation we're going to make is that really this ds distance that we talked about up here and dx are really very close. In fact, we're going to assume that they are the same thing. So now that, as you can see, their derivative becomes dx, from ds to dx. And again, now we have the derivative of the slope is equal to the curvature. So again, if we differentiate both sides, we now know that the curvature is dy dx. That we knew already. So take the derivative of both sides, we get this. And now you can see there's our displacement that we talked about before. And now it's related directly to curvature. So now we have a displacement curvature relationship. So now we just need to get curvature related to something else that we know. So in this case, we're going to do that to moment. So let's look in general at how a shape behaves. So here's a general cross-sectional shape about the neutral axis. And you can see that when that shape bends, the bottom in this case will go into tension, the top in compression. And we're going to assume that this face that we started with right here is going to rotate through that angle d theta that we talked about before. That face is going to stay nice and linear. And what's causing that rotation is moment. So this is how we're going to get our moment curvature relationship. Okay, so if we look at this top little bit here, this dl, that's how much it rotates and displaces that top fiber. And we're going to get it in terms of d theta. And we can do that by using c, which is the distance from the neutral axis to the top fiber. And we can do that through this relationship. So again, just like we did the arc distance before, the arc would be d theta, the radius would be c, and that arc distance would be dl. So that's the relationship we're using to get the change in the top fibers as a function of theta. Now we know strain on the top fiber is the change in length, dl, over the original length, dx, right? Change in length over original length. And we know that dl from that previous thing can be related to theta. So I can rewrite all that and now say that really strain, is the first derivative of slope times c. Okay, let's hold on to that for a second. We also know curvature. Remember we had our relationship we talked about before. We knew that the derivative of the slope was equal to the curvature. And now we know that strain is also equal to that same derivative. So we can put those two things together. So now I know the second derivative of y, which is the derivative d theta, and there's d theta again. I can rewrite it now as strain over c. That's pretty good. So we're moving now towards displacement strain. Now we're doing linear elastic materials, so we knew Hooke's law. We have stress versus strain. So we can relate it to this way. So now I can plug that in there, and now I have what? The second derivative of displacement is equal to stress over E, and then there's C. Okay, that's pretty good. Well, we know from Mecha Materials that stress is the moment times C divided by I. I know that's a very bad symbol. It looks like a L, but that's actually a capital I in Arial font. So that's capital I, moment of inertia. Plugging that back into the other expression, we now get this. So this is a lot of work. We've gone through quite a few minutes here of discussion, actually me talking. And now you see that the second derivative of displacement is equal to m over EI. And that's pretty powerful because you guys can write moment expressions. You've wrote equations for moments as a function of x. And now you can see that that really is the second derivative of displacement. So that means that if I integrate both sides twice, I can get an expression for displacement. So that means we can go back to our ability to write moment as a function of x, integrate it twice, handle the integration constants, and now I can get an expression for the displaced shape. Pretty powerful. So all this previous discussion up to this point just brings you to this. This is the big blue box. That's what we want. That's the only relationship that you need to remember moving forward. So how do we use this? Okay, how can we use this equation to solve for displacement? So again, if we can write an equation for moment, integrate it twice, we can get displacement. So let's work an example problem where we do that. Oh, by the way, this is called direct integration. This is the first method that we're going to use. And it relies on the fact that you can write a continuous function for moment over the beam. Okay, so here's an example. Let's look at this particular beam. We've worked this kind of problem many different times. It's a cantilever beam. You can see on the left, fixed connection. On the right, we have a moment P. I know you guys don't like these problems with symbols, but this is pretty powerful. We have a load P and length L. So this is basically any in-loaded cantilever beam problem. So remember our basic direct integration law or rule is we first need to find the moment expression. So let's write moment as a function in this beam. All right, so here we go. So I'm going to find the reactions of the beam first. So you can see I'm going to assume here at A, I have a reaction in the vertical direction, and I'll assume a moment at A. Both those, this is a positive bending moment, and this is a positive shear force. So I'll go ahead and sum moments about A. So now, using right-hand rule for my sign convention, you can see here, this moment that I assumed here, which is a positive bending moment, is actually a negative moment because I'm using right-hand rule. You can see here, there's my right-hand rule. And then about A, this load over here at P is creating negative moment 2 with the moment arm of L. So it's pretty easy to find my reaction for the moment. It's just minus PL. So it's a negative bending moment at A. So far, so good. That seems reasonable. And just in case you forgot, you'd expect that with this beam, with this load here, it would go down. And then, of course, with no slope, we should have a deflected shape looking something like that. So you can see this is kind of a frown, concave down, negative moment. That makes sense. Go ahead and sum moments forces in the y direction. We'll assume up is positive. You can see that I have my AY reaction up, my P force is down. So when I solve for that, I find AY is P. And both those results seem reasonable. So we found our reactions. So now let's write the equation for moment in this structure. So there's my P, and there's my moment. So I've corrected the sign. So I got a positive shear force, negative bending moment. Then we're going to come out here at some distance, x. I'm going to cut the beam, and at the cut, we're going to assume positive shear force, positive bending moment. And we've been doing this quite a while now. This is our method of sections. We've done this for a couple of weeks, maybe months now. So now I just have to find these. And really what I'm interested in right now is that moment expression more than anything. So I'll sum moments at that cut section. And you can see, again, I'm assuming right-hand rule for my sign convention. So I have the moment, which I assume in this direction. It's a positive bending moment. That's a positive moment in my sign convention for statics. Then I have P going through a moment arm of L. That's creating negative moment about the cut. And then I have the actual applied moment over here, the reaction moment, PL, which again, from my sign convention, that's positive. So then I solve for what I don't know, which is the moment. And when I do that, wrong direction. When I do that, I get the moment is P times X minus L. Now we can check that. Just like we've done before, it's important to check the validity of your moment expression. So we know when x is equal to 0, that's here, we should get a minus PL. And if you plug in x equals 0 here, you do get minus PL. Also, you might remember this was a cantilever beam, and the free end of the cantilever had no moment. And that was at x equal L. So if you plug in x equal L, you do get 0. So that seems to work. So I think my moment expression is valid. So now I just need to integrate. There's my moment equation. So shear is m over EI. So I'm going to integrate that. So you can see there's my moment equation plugged in right here. And this is a simple polynomial to integrate. So I'll do the integration. So you can see x becomes x squared over 2, and then L is a constant, so I get Lx. And this is something that you're probably not used to much if you've been out of math for a while, is this is an indefinite integral, so we generate an integration constant. So you have to ask yourself, hey, this is an equation for slope. Slope. Do I know anything about slope? And in this particular problem, you do. We know the slope at the fixed connection. And slope of the fixed connection is 0. So I'm going to use that to solve for this unknown integration constant. So I know that the slope at x equals 0 is 0. Now this is not true for every problem. This is true for this problem. So now I can plug in x equals 0 here and force this whole expression to be 0. And when I do that, I find out that x1 is 0. So really x1 is eliminated. So now this becomes my expression for slope. And it's easy to check. Again, if I put in x equals 0, 0, 0, I get 0 slope. It does match my boundary condition. But I can put in any value I want here for x, any value from 0 to L, and compute the slope anywhere I want in the beam. That's pretty powerful. So in this case, I went ahead and computed the slope at x equal L, which is the free end, and that's where the slope is maximum. And you can see I get a negative slope, which makes sense. And the value is PL squared over 2EI. If you check the units of this, you'll notice that P is force, L is length squared, so you get force length squared on the top. E is force per length squared. I is length to the fourth. So both those numerator and denominator units are force length squared, which basically they cancel out. So again, our slope has no unit here, so it's dimensionless. And mathematically, that will be in radians. So now all I have to do is integrate this one more time, and I'll have my displacement equation. So let's integrate that. So I now have an equation for slope. I'm going to integrate it and find my displacement equation. So I'll plug it in. Let's do the integration. Again, polynomial integration is not too hard. So x squared over 2 becomes x cubed over 6. Lx becomes Lx squared over 2. And then there, generate a new integration constant. Now this one I need to know something about displacement. So where do I know displacement anywhere in the beam? Well, in this problem, I know it at x equals 0, the fixed connection. So again, I plug in x equals 0. Everything is 0 except for C2. So that means that C2 also has to be 0. And when I'm done, there's my equation for displacement. And that's the displacement anywhere I want in the beam as a function of x. So again, you can see this condition is still checked when I plug in x equals 0, 0, 0, x is 0. So this is a cantilever beam, so probably the maximum displacement would occur at x equal L. So I went ahead and computed that. And again, there you can see the expression. It's negative, so it is down, but that confirms with what we've done before. And now look at these units. So I got force length cubed, and in the bottom I got force length squared. So this will come out with units of length. So if I do all my length in inches, my displacement will be in inches. If I do all my units in millimeters, my displacement will be in millimeters. Okay, so what I have next for you, I'm not going to do it in this video, but if you look online and look at the other videos, I'll work this problem, one with the distributed load across the whole beam, and we'll do direct integration. And then I will do one with a triangular varying load using the same method. And then the last problem, a little trickier one, um, we'll work this problem. Now, what this problem shows is kind of an interesting challenge is I cannot write a continuous moment expression for the whole beam. Now, if you got this problem as part of exam one, you'd really like it because this is an easy problem to find the two moments. You just have to keep track of it. So I'll have a moment, say M1 for the first third of the beam, and then I'll have a different moment for the final 2/3 of the beam. So this one's a little trickier to do. You'll get 2 integration constants for this one and then 2 more for this one. You'll have to match them at this appropriate place. And this is a disadvantage of direct integration. It makes it a little more challenging to do. So as we move forward, I'm going to constantly talk to you about advantages and disadvantages. So anytime you can write a continuous moment, say something like this, or even this one, then one moment equation, couple integrations, couple evaluation of integration constants, and you're done. Problems more like this one, oh, my highlight stayed, a little more challenging. So look at the videos on that. I'll talk about the challenges of doing this and show you that solution. Okay, so I'll stop sharing my screen, come back to the main window, and wish you good health and hope everybody's doing well. And let me know if we have any problems. Don't forget to email me or call me. I gave you my home phone number. Please do that. And maybe on later in the week or beginning next week, we can have, we'll try to do a Zoom session, maybe just for questions. So I'll let you guys look at the videos and see what you think. And then if you have any problems or questions, we can have a meeting and we can go from there. Okay. Well, have a good day. Bye.